Welcome. Today I'm going to talk to you guys about reflection. And reflection is actually one of those wave behaviors we've mentioned a few times. Turns out it's not really just a wave behavior. Things that are not waves tend to reflect off things. For example, if you've ever thrown a ball against a wall, you know that a ball on the big scale is not a wave, and so the ball does reflect off of the wall, and you can imagine that little particles might do the exact same thing. So we call it a wave behavior, even though it's technically not necessarily a wave behavior. But light does it, and it's one of the more familiar phenomenon with light. So we want to talk about that just for a little bit, if we can. So I put down some quick notes here, right here at the top. You can see it says there are only two ways to see objects. Either they make their own light or they reflect light. Now I want you to think about that. As you're thinking about the things that you see on a daily basis. Are you seeing them because they're making their own light or because they're reflecting light? And the answer to that is that probably 99.9% of the time, the objects you see are reflecting the light from other sources. And so as a result, we have to try to talk about what that means. And so reflection is kind of crucial for how we interact with the world around us or take data from the world around us. So I want you to imagine over here. So we've got a light source right here, and then we've got here. We'll start off with this guy over here being our observer. Okay, and so the observer is standing there looking over at somebody else. Now this person right there is not producing light of his or her own, and so as a result, we have to sort of infer that they must be reflecting light. And so what does that look like? Well, if you go through here, you can see that what must be happening is that light of the blue wavelength, so little wavelengths of light like this, must be hitting off of the shirt and then moving off into space. And so what you can see is you've got all these blue wavelength lights going like so. Now we find out as we talk about this that light waves move in straight lines. And so as a result, I will typically draw them out as a straight line rather than having to wiggle like this. There we go. You get the idea. So this guy's shirt appears blue to the observer. I tried to draw it blue so that you could get that idea. And so I've drawn blue light waves here as hitting the shirt and then reflecting off. Now you might notice that some of them get reflected off in some directions and some get reflected off in other directions. And as a result, we kind of, our eye picks up all sorts of different light waves coming from all the different areas of the shirt and tries to integrate them into a picture of what the shirt looks like. And so we have in our heads a picture of what that's looking like based on the energy that we get from these waves based on their wavelength. And so we can see that they're blue because they have the blue energies, and as a result, we put this picture together in our heads of what that shirt looks like, and well, we say it's blue, and it's because of the fact that it's reflecting the blue light. Now, what happens if red light hits it? So red light also coming down. If we assume this is a white light source, it hits, and then what happens to it? Well, typically, not always, but a lot of the time, that red light is going to be absorbed. And so the energy that it carries with it gets absorbed into the shirt and is turned into the thermal energy and is not reflected. And that's why we don't see the shirt as being more red. We could change the color to something else like green in the middle of the spectrum. And that's a really big one, so I'm not going to do that. Let's see if we can make it a little bit smaller here. There we go. So if I have a green light source, the green typically would hit and absorb as well. And so as a result, we see the blue is reflected, but the red and the green are not, and they are absorbed. And so as a result, we only get the blue light. And as a result, the shirt appears blue to us. So that's why things appear to be the color that they are. If they're not exactly blue, but there's some sort of intermediary color, you can imagine that some of the light that you get that gets reflected off is blue, and some is red, and some is orange, and some is whatever. You get the idea. And so you can mix those colors together in your head and make a composite color somewhere in your brain. Hopefully that makes sense. But the light that gets reflected off gets reflected off in all sorts of different directions because of the fact that the shirt is not very smooth. So you can imagine if you took a look at it really up close, the even really smooth fabrics, you'd see this very intense variation in the surface. And as a result, what happens is the light waves come in, and instead of getting, I'm going to draw them as rays this time. So let's say I have a light ray coming in here, like so. It gets reflected off. Now you can see that that little bit of surface right there is kind of angled, and so as a result, it might get reflected off like this. Whereas another light ray that's coming in from the same source, so coming in like so, you can see hits that surface right there, and so may be reflected off like so. And we can keep doing this. So all these parallel light rays that come in get reflected off like so. And so you can see that they're sort of spread out. They're scattered about. Not in the same scattering as what happens in the sky, but the same idea, kind of, is that the light rays end up going in all sorts of different directions. We call that diffuse reflection. Anytime you can see color coming off of an object, but you can't really see an image in the object. So, for example, you can't look into a shirt and see your own face staring back at you, typically. That's a diffuse reflection type situation because it's reflecting all over the place. It's diffusing out the light. On the other hand, there's these things called mirrors, and really anything that's sufficiently smooth and typically metal has a tendency to do this kind of thing. And so as a result, what you see is that you have a light ray coming in, and it's a nice smooth surface. In fact, it has to be about as smooth so that there's not as much variation as less than 1 wavelength of light. So you can imagine that has to be pretty smooth. And then it gets reflected off. And so as a result, we can do the same thing. Another light wave comes in parallel to the first, and it leaves parallel to the first. Again, light wave comes in parallel to the second, and it leaves parallel. And so you can see that because of the fact that the surface is very smooth, it ends up parallel light rays that come in end up being parallel as they leave. As a result, we can come up with what's called the law of reflection. The law of reflection is a very easy one. It says that for any surface, if you draw a perpendicular line to this little local region of the surface, what you see is that the angle that you measure, I'm going to change my color here, over to my custom pen again. The angle that you see here between the light ray as it comes in and the perpendicular line to that surface, we call the angle of incidence. So theta sub I. The angle of incidence means to fall on something, so the angle of incidence, and the angle of reflection, so on this side, theta sub R, have to be the same. And so the law of reflection states that theta sub I equals theta sub R. That's the law of reflection. And again, this works all the time. What is weird, though, is when you have diffuse reflection, you have to remember that the perpendicular that you draw, in other words, the normal line, if you wish, ends up being kind of all over the place. Look at the normal line here. If I go back to this surface again, here's a normal line. And then for this part over here, here's a normal line. And then down here, here's a normal line. And 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 you can see, so the normal lines are all scattered about. And so you shouldn't be surprised when you get this kind of spreading out of the light waves as a result. So that's where that's at. Now again, if you can see your image in an object, then you are probably getting this specular reflection. And if you can't, you're getting this diffuse reflection. Either way, they still behave according to the law of reflection on the microscopic scale. So this little surface right there is what's going to determine how the light ray that's hitting it gets reflected out. And the perpendicular line between that little surface and at the point where it gets hit is going to determine what the angle of incidence is, which then, of course, determines the angle of reflection. So that's really it. We're going to talk more about how you can make images in mirrors later on, but for right now, that's the big stuff. If you have questions, please let me know. Thanks for watching.